It is my pleasure to introduce Alex Iosevich back at the Graduate Center again. Discrete energy and applications to Erdos type problems. Go ahead. And let me encourage everyone who's not speaking to mute themselves.
Okay. Oh, yeah. I was about to mute myself, but that doesn't make any sense. Okay. Excellent. It's a pleasure and an honor to be here as always. It's great to see so many old friends. I'm going to talk about a very, very simple topic. It's something that I've talked about many times. Most of these things you've seen before, but the idea to give a talk on this topic was triggered by roughly two things. One is a conversation I had with Mel recently about a very nice paper that he wrote about certain summations that arise over Cantor sets. And second is that last summer, I ran a data science REU. And in the process of running that program, an idea arose about using certain objects from geometric measure theory and geometric combinatorics for the purposes of dimension reduction problems. So this is something that I will eventually be ready to talk about, but I'm maybe a few weeks away from that. So for now, what I am going to talk about is I'll remind you of what the discrete energy is, some of the basic results, because I often talk about applications of these concepts, and I very seldom talk about what's sort of underneath the hood. And as I said, hopefully sometime in the near future, I can start talking about the data science applications of these things. Okay, so what is the basic idea? So this is the main theme of this talk. So let P be a discrete subset of the unit cube. So D is bigger than or equal to 2 of size n. Okay. And so now we define the discrete energy. And one thing that I want to say that is that one could easily give a semester-long course on discrete energy. This is a subject that's been studied by many people. Books have been written about it in a variety of contexts, right? So I'm not even going to attempt to put these things into a broad context. This is a subject for a different day. But in the context of this talk, we'll talk about discrete energy as follows. So P is a finite set. It's a subset of the unit cube. This is not essential, but I just want to fix the set where we're operating. It's of size n, and we take the summation over P not equal to P prime. Keep in mind that P and P prime are vectors. Then we take a distance from P to P prime to the power of minus s and divide by n squared. So you just normalize it. Okay, so this is a discrete energy. Okay, so it's an attractive looking summation. The question is, what is it for and what does one do with it? And as I said, it's been studied in a variety of contexts.
Excuse me, which distance are you using? What's your definition of distance?
Of distance? This is a Euclidean distance, but in this particular context, it does not fundamentally matter. But we are using the Euclidean distance. In many of the problems that I talk about, including some of the problems I'll mention later today, the distance function very much matters, but not in this particular context. But we are using the Euclidean distance just to fix the definitions. Okay? All right. And so what I'm going to focus on is an idea that I've been playing around with in one form or another in a variety of contexts, most of which I'm not going to have time to mention, and that is how to apply continuous results from geometric measure theory to yield discrete results in geometric combinatorics. And people have asked me many times, students, colleagues, whatever, how did I get into this sort of area of applying continuous results in a discrete setting? And the answer is very simple. In the late 90s, I stumbled into combinatorics problems. And when I stumbled, I mean, I really stumbled. I tripped over and my nose hit combinatorics. I was working on a completely respectable functional analysis problem. And that was the question of whether L2 of the bow has an orthogonal basis of exponentials. And for some crazy reason, this very natural looking question was open at the time for over 20 years. And it turns out that the reason that it was open is because it's not a problem in analysis at all. It's a rather trivial problem in combinatorics. And this convinced me that combinatorics is a very worthwhile subject, and I never looked back. Okay, so then I said, all right, I'm going to work on combinatorics problems, but I know nothing about it. So what am I going to do? Well, I decided that I do know something about Fourier analysis. So I tried to look for ways of converting Fourier analysis results into combinatorial results. And this is partly what this talk is about. Okay. So let's begin by putting things into context. So eventually we will be converting continuous results into discrete results. So I already described the discrete energy. Okay. And now let's describe how energy arises in the continuous setting. So mu is a compactly supported Borel measure. And we define this double integral in place of a double sum. And also mu is a probability measure. So norm x minus y to the power of minus s. S for us is going to be a non-negative parameter, though in principle doesn't need to be. But in our context, it's going to be a non-negative parameter. And then d mu x, d mu y. So at least from a visual standpoint, this is clearly an analog of the discrete quantity I wrote down here. Or more precisely, since the continuous variant almost certainly came first in this particular instance, this is a discrete variant of the continuous energy. And so I'm not going to describe this very precisely, but here's one way that energy integrals arise in geometric measure theory or analysis, is that if E is the support of this measure mu, then the Hausdorff dimension of E can be determined, roughly speaking, as the sup over these indices S, such that the S energy integral is finite. So so for those of you who are sort of very well familiar with fractal dimensions, this is, I think, a very fascinating subject, because there's several notions of fractal dimension. There's, for example, Minkowski dimension, which is, roughly speaking, about covering your set with balls of a fixed small diameter. So it's a counting problem. The dimension becomes a counting problem. The Hausdorff dimension is a much more subtle thing. It is about this integral over here. And this integral was originally, at least as far as we know, invented by Newton in the context of measuring electrostatic interactions. So Hausdorff dimension is not just about size, it's about how mass is concentrated. And this idea is very much going to come into play when we discuss the discrete manifestations of this phenomenon. So one thing that I forgot to say, and that I usually say in the beginning of my talk, is please interrupt me anytime for any reason. If I cover less in the talk, then so be it. All right, so what we have just seen is that the classical S energy determines Hausdorff dimension. So the question is, what does the discrete energy measure? And instead of writing down complicated theorems or mildly complicated theorems, let me just perform a trivial calculation, which gives you immediately a feel for what is going on here. Okay? So let's take our set to be just a diagonal, j over n, all the way up to j over n, where j is less than or equal to 1 and n. So these are equally spaced points on the diagonal of the unit cube. Okay? So let's compute the energy of this object. So the discrete energy is what? It's once again 1 over n squared, summation over p not equal to p prime. So these are the points from the set to the power of minus s. And just plug in the definition. This is 1 over n squared, summation over j not equal to j prime of absolute value of j minus n minus j prime over n to the power of minus s. Okay. Well, let's unravel what this is. This is n to the power of minus 2 plus s. I insist on making this completely transparent. So this is n to the s, it goes upstairs. And then you have a summation over j not equal to j prime of the distance from j to j prime to the power of minus s. Okay. So then you make the obvious substitution, and you have twice n to the minus 2 plus s. And then you have a sum from k equals 1 to n minus 1 of k to the minus s, but you also have to count the number of pairs from 1 to n, so that j minus j prime is equal to k. Okay, and what is this? The number of such pairs is approximately n. So you're left with n to the minus 1 plus s, summation from k equals 1 to n minus 1 of k to the minus s. And, well, when is this quantity bounded independently of n? It is bounded independently of n if and only if s is less than 1. If s is bigger than 1, the sum converges, but then you lose here for more obvious reasons. If s equals 1, the summation of 1 over k diverges, in spite of what some of my students asserted on the last midterm. Okay. And so the idea here is that this quantity is bounded independently of little n if and only if s is less than 1. So in analogy was the continuous case. I decided not to write any fancy definitions in this talk at all. Just try to talk about the substance of the matter. In analogy was the continuous case. This suggests that capital P is one-dimensional. Okay? In other words, this strongly suggests that discrete energy measures at least some of the same phenomenon that its continuous analog does. Of course, all of that needs to be made precise in a given context. Okay, everything cool so far? Sorry if I'm talking a little bit slowly and asking for questions. It's just that I'm teaching calculus for biological sciences this semester, and I'm in that mode. Okay. All right. So in the example above, the points on the diagonal are evenly spaced, okay? But it's not difficult to see at all that the energy integral only gets larger if the points are not evenly spaced. Okay, this is really the best case scenario. And you can summarize this idea as follows. And this is work in progress stemming from the summer program that I mentioned. Much of this work is computational and much of it is applied, but there are a few theoretical components, and this is one of the lemmas. It's not very difficult, but I think it's sort of an important illustration of what I'm talking about. So, so let Pn denote a family of sets of size n contained in the closed interval 0, 1 to the d, so d-dimensional cube. And suppose that it happens to be true that these point sets are subsets of a k-dimensional manifold, where k, of course, is less than or equal to the ambient dimension d. Okay? Then ik of Pn is not bounded independently of n. Okay? So, and in particular, is for any s bigger than k is not bounded independently of n. In other words, if a point set is a subset of a k-dimensional manifold, then with respect to discrete energy, this point set, or rather a family of point sets, cannot be better than k-dimensional. This is a sort of a heuristic point of view on this. Okay? Quite likely, one can replace a manifold of dimension k by any compact set of Hausdorff dimension k. I do not expect this to be difficult, but I can't assert it until this is written down. I was hoping this would be written down, but then elections got in the way. All right. So one of the things that I want to move towards is applications of this concept in discrete geometry. And in fact, there will be a tiny bit of an overlap between this talk and the last talk that I gave on CUNY, also on Zoom last May. Okay. So we say that Pn in the unit cube, d-dimensional unit cube, is a homogeneous family of sets if there exists constants little c and big C with the following properties. The points of capital P are n to the minus 1 over d separated. And so what I mean is Cn to the minus 1 over d separated. And every cube of side length capital C n to the minus 1 over d contains at least one point of P. Okay, now when definitions are flashing in front of you on the screen, it is sometimes difficult to absorb them in real time. So what is this definition saying? Let's simplify it a tiny bit, not much, and then it becomes completely visually transparent. All we are really doing, more or less, is taking the d-dimensional cube and breaking it up into n cubes of equal size. And what we are assuming is that our set Pn has exactly one point in each of those little cubes, and no more than 1 point, say. Okay, this definition is slightly less restrictive, but this is the general idea. The point here is that the set behaves statistically like a lattice, but may not have any of the lattice's arithmetic properties. So this is not about arithmetic. Okay.
Sorry, Alex, this is probably a stupid question. What's the role of the n here?
Oh, in the definition of homogeneity?
Yeah, yeah.
Oh, so the points are n to the minus 1 over d separated.
So is P sub n the...
P sub n has n points in it. So
it's just the cardinality.
Yeah, it's just a cardinality of the set.
Okay, thanks.
This is how I defined it before. I really should have defined it again. So it's a very good
No, it's
question.
my fault. Thank you.
No worries.
Again, Pn is one set, or Pn represents one of any number of possible sets.
Sure.
I mean,
P sub n
family
is
of sets or a set?
It's a family of sets, and each of these sets has n points. Now, for the purposes of applications of these things, we don't really need this defined for every integer n. So you can think of this as a sequence of n's going to infinity. But for the time being, P sub n is a set containing n points. And so we have a family of such sets. We're talking about asymptotic quantities here, so we don't want to fix the set, at least initially. Make sense?
Yeah, isn't there a concept of net or something like that, which is very similar to this?
Absolutely. But I am extremely allergic to notation. In fact, in this set, not only am I avoiding other people's definitions, I'm avoiding my own definitions, as people who have seen talks on this topic will see in a moment. But you're absolutely right.
One more stupid question from me, and then in the second line, the set P, is this just the same as Pn? Is that just a...
This is Pn. This is simply a typo. This is a result of typing the talk while watching election returns.
Okay.
Okay. So you're absolutely right. Okay, so this is a theorem, and maybe you should really, I think it's really a lemma. So let Pn be a family of homogeneous subsets of the cube. So each has n points. Then for any s in the closed interval 0d open, the discrete energy integral of Pn is bounded independently of n. Okay, in other words, what we are saying is that a homogeneous set is in the d-dimensional cube is d-dimensional in nature. This is not a shocking statement, but what it does is it puts these things into context, number one, and number two, it's going to allow us to apply this context, this notion later on. Okay. All right. So here's another theorem. So this is from way back, and this was joint work. This is joint work with Misha Rudnev and Ignacio Uriarte Tuera. I misspelled Ignacio's name. I will again blame this on election returns. So given S naught in interval 0D, there exists a nested family of sets P sub n, we can even make it nested, of size n, such that the S discrete energy is bounded independently of n for 0 less than or equal to S less than S naught, and unbounded if S is bigger than or equal to S naught. In other words, for any S naught in the interval, we can create such a family. So this notion is not tied to some particular interval of indices. And this is where a connection with Mel's recent paper lies, even though I'm not going to describe it in great detail. So this can be proven in many different ways, but the simplest way to prove this is to consider the endpoints of the mth stage of a construction of a Cantor set, where you choose the dissection ratio in such a way that the Hausdorff dimension of the set is S naught. Okay, in other words, you can play around with the dissection ratio to make so I wrote here Hausdorff dimension, but for Cantor sets, all notions of dimension, okay, one should not be quite so flippant, but all reasonable notions of dimension coincide, okay? And so in that case, it's not difficult to show that the S energy of the resulting discrete set is easily seen to be bounded. Well, I don't know about easily, but it's not very difficult to see that it's bounded independently of n, if and only if S is smaller than S naught. And so one comment now is that if one sort of gets underneath the hood of this, you'll start getting sums that are very similar to the ones that you've studied in your paper. Okay, so now let's go ahead and see the connection, see some connections between this and these discrete energy and geometric combinatorics. So the Erdos unit distance conjecture, this is what I talked about in my last talk in May, at CUNY at May. So if P is a finite point set in the plane of size n, then the number of pairs such that separated by distance 1 is bounded by n. What this notation means is that one squiggle means that we are absorbing constants, and the second squiggle means that we are absorbing arbitrarily small epsilons. Okay, so there could be log terms buried in here. One can formulate this conjecture more precisely, but we're so far from solving it, it's really not the point. Okay, and so the left-hand side here can be viewed as the number of incidences between the points in P and circles of radius 1 centered at the points in P. Okay, and just as a reminder, just to put things into context, it's a variant of the Zamaretti-Trotter incidence theorem due to Chung, Zamaretti, and Trotter, I believe, yields that the number of these pairs separated by distance 1 is in fact bounded by constant times n to the power of 4/3. But as I never cease marveling, nobody knows. Okay, so this paper was published in the early 80s, if I remember correctly. And please correct me if I'm wrong. But
I might be wrong myself, but isn't it Spencer, Zamaretti, and Trotter, this one? Joel Spencer?
It's Spencer, Zamaretti, and Trotter. Chung did spheres and points.
I am sorry. I am sorry. My apologies to Spencer. I did not mean to slight him.
Luckily, he's not here. No.
Huh?
Luckily, he's not here, so that's
no.
fine.
But these days, everything is recorded. No, I'm kidding. But I'm sorry. I am sorry. Yeah, this is Spencer, Zamaretti, and Trotter. So they established this constant n to the 4/3. It's essentially the same proof, especially from sort of a modern point of view on these incidence theorems. It's the same proof as Zamaretti, Trotter. And nevertheless, there's been absolutely no improvement on this problem since then. I mean, to the best of my knowledge, there's literally no improvement, not even on the level of constants, right? I mean, this is annoying as hell. Okay, and so here's an interesting variant of the unit distance problem. and that is to obtain bounds for the number of pairs, not separated by distance 1, but separated by distance between 1 and say 1 plus delta, okay? And so delta is a small threshold, P is again a finite point set, and it is completely clear, of course, that you cannot get anything interesting if delta is large enough. But what happens if delta is small? If delta is small, then there's a variety of things you can say, and the talk that I gave in May was entirely dedicated to that. I'm not going to repeat things that I said back then, but nevertheless, this point of view is going to be useful in illustrating this discrete energy that I'm talking about. So now let's consider a continuous analog of this problem. And this was established, so I'm stating it here in R2, but I'll also mention a higher dimensional result in a moment. So Falconer proved that if mu is a compactly supported Borel measure, then the mu cross mu, so the measure of the set of pairs separated by distances between 1 and 1 plus epsilon, is bounded by a universal constant times epsilon times the continuous energy integral of mu of index 3/2. Okay, so once again here, the continuous energy is this double integral of norm x minus y to the minus s d mu x d mu y. Okay, and stating the problem in this way allows us to talk about it quantitatively instead of talking about it in terms of Hausdorff dimension. So this is another theme that's going to come up a few times in this talk, is that, so there's this tendency, I think, in all fields of mathematics to try to state the results elegantly, right? So many results in geometric measure theory are stated in the form, if the Hausdorff dimension of a set is bigger than that, then this happens. But what you actually prove typically is a much more ugly looking quantitative statement, okay? And what I'm going to say is going to rely on that to a significant extent. So here it's interesting to note that the exponent 3/2 is sharp. So this was established by Mattila, and there's been considerable amount of work on this in higher dimensions done by Steve Sanger and myself. But one thing that is interesting to note is that, as you'll see in a moment, when you translate this continuous result into a discrete setting, you get something that corresponds to the Spencer-Zamoretti-Trotter bound for the single distance problem, not the conjectured bound. And one might wonder, and in fact, Steve Sanger and I wondered, whether you can recycle these continuous counterexamples into discrete ones. And it turns out that the answer appears to be no. So I'm not going to describe Mattila's example, but his example is very much continuous in nature. It cannot be discretized to yield any reasonable counterexamples in the discrete setting. Okay, so here's what Falconer's result implies. And I'm going to describe the mechanism of this, the so-called continuous to discrete conversion mechanism later in the talk. So, and this appeared in the context of much more general results in the joint work with Hadi Jarati and Isabella Laba. And I think that paper appeared around 2010, but I don't remember. So let Pn denote a family of discrete subsets of the unit cube, once again of size n, such that the discrete energy of P sub n is bounded independently of n. And let S be bigger than or equal to d plus 1 over 2. Okay, so d plus 1 over 2 is the exponent that arises in the continuous setting in higher dimensions. In 2 dimensions, it's 3/2. In higher dimensions, the same result holds, but you have to replace 3/2 with d plus 1 over 2. Okay, and so let S be bigger than or equal to d plus 1 over 2. It's that threshold that I just described. then the number of incidences between the points of Pn and annuli of radius 1 and thickness n to the -1/s centered at the points of Pn is bounded by a constant n to the power of 2 - 1/s. Okay, so one thing to note here is that if you're in 2 dimensions, and S is, so then S is 3/2. If you plug this in, this is 2 minus 2/3, which is exactly 4/3. In other words, in 2 dimensions, what one recovers is a variant of Spencer-Zamoridi-Schroeder. It is stronger in some ways and weaker in others. It is weaker because it doesn't apply to all possible point sets. It only applies to point sets satisfying this discrete energy condition. Okay. On the other hand, it is stronger because it yields a result. It yields a result for incidences of points and annuli, not just points and circles. And those are much more difficult to get. There's another way in which this result is difficult to duplicate using discrete methods. And that is here, the result is stated for specifically for Euclidean circles or annuli based on Euclidean circles. But the truth is the proof doesn't change if we replace a circle by a unit circle in any norm such that the boundary is smooth and has non-vanishing curvature. So a parabola or an ellipse or any even uglier object, as long as it's smooth, it doesn't need to have any symmetries. As long as it's smooth and has non-vanishing curvatures, this machinery works. Okay. And so now this brings us to another point, which I think is quite fascinating. And this is a point that Steve Sanger and I explored quite a bit also. And that is that in this result is stated in all dimensions, right? And at this point, if you're familiar with incidence theory, you might be saying, wait a minute, how could this be? In dimensions 4 and higher, there's the celebrated lens example, which is an example of a set of n points where the unit distance repeats n squared times. Certainly is not bounded by constant n to the 4/3. But then the whole point is that this is where the discrete energy condition really kicks in the big way. So let's take a look at the lens example and see what's going on. So just as a reminder, here's how the classical lens example works. You put n/2 equally spaced points on capital A and capital B respectively, where what is capital A? It's cosine theta, sine theta, 0, 0. And capital B is 0, 0, cosine phi, sine phi. In other words, in the first set, you put a circle in the first 2 coordinates. And in the second set, you put a circle in the second 2 coordinates, right? It's in retrospect, a simple idea, but many brilliant ideas are in retrospect simple. And this idea by lens is just absolutely wonderful. So then the number of distances between any point of A and any point of B is square root of 2. So this yields the trivial n squared bound for the unit distance problem. If you measure a distance from capital A to capital B, right, then this distance is just square root of 2 throughout. So the distance square root of 2, which of course we could have scaled down to be 1, is n squared, and one cannot do better. So what is the problem here? Why doesn't this contradict the result that we just stated? So just to recall, on the previous page, we stated this result here in any dimension, and it's a non-trivial bound on the number of incidences between points and annuli. But the point is that this set, capital A, and the set capital B, these sets are inherently one-dimensional. Now, the ambient dimension here is 4. So the d + 1/2 is equal to 5/2. In particular, these sets do not satisfy the discrete energy condition if the discrete energy condition in the range S bigger than or equal to 5/2. And this explains how Len's example can logically coexist with the problem that I just described. Okay? Excellent. All right. So just before I move on to the application of this discrete energy to the Erdos distance problem and its close cousins, let me just mention in passing, and this I'm going to talk a lot more about once I start giving talks on the applied aspects of this theory. But so we've mentioned that if a set is a subset of a manifold of dimension k, or even a subset of most probably a set of Hausdorff dimension k, then there are limitations on when the discrete energy can be bounded. But there's another source of examples, and that is sets that are badly clustered. And they do not need to satisfy any particular dimensional. In other words, they don't need to be subsets of any set of a given dimension or anything like that. Basically, if you take a set of n points, which is divided up into clusters, these sets can fool the discrete energy into believing that we're dealing with a set of a lower dimension. Okay, and this is just sort of a note in passing, precisely why these discrete energies may be useful in data science, in the study of dimension reduction, dimensionality of sets in general. Okay, so for the final stretch of this talk, I'm going to describe, and some of you have seen it before and some of you maybe have not, is I'm going to describe how one uses the discrete energy inside the continuous to discrete conversion mechanism, which allows you to take certain results in Fourier analysis or geometric measure theory, if you will, and convert them into results in discrete geometry. Okay? Okay, so let Pn be a family of n minus 1 over s separated point sets in the unit cube of size n, such that the S energy of Pn is bounded independently of n for S bigger than S naught, with S naught to be determined. Okay? And what I mean by for S bigger than S naught, for some S bigger than S naught. Okay? And suppose that we want to estimate from below the number of suitably separated distances determined by Pn. Okay? So in other words, what we have initially is a perfectly classical discrete problem. We have a set. Well, just for normalization purposes, we're putting it inside the unit cube. We're also assuming that it's n to the minus 1 over s separated, and that the S energy is bounded for some S bigger than S naught, okay? And so here's how we do it. So the idea is to reduce a discrete result to a continuous result. So step one is that we put each set in disguise, because we need to pretend that we're dealing with continuous quantities. So we define this measure mu ns of x as 1 over n. We're simply normalizing by the number of points. Then we take n to the power of d over s. I'll explain what that is in a moment. And then we take a summation of psi of n to the 1 over s x minus p, as p ranges over our point set. In other words, we simply take a ball of radius n to the minus 1 over s. We do it in a smooth way, but this is just for convenience, around each point of the set. And so we take a sum of these point masses. Well, they're not quite point masses because these are balls. And then we normalize it so that this is essentially a probability measure. To make it really a probability measure, we would have to divide, multiply by an appropriate constant. Okay? Then the next step is, suppose that one has a result which says that if E is a compact subset of Rd, equipped with a measure mu with a finite energy integral, then the Lebesgue measure of the distance set is bounded from below by a positive constant. Okay? In other words, this is a statement of a Falconer type problem. But as I mentioned, so the Falconer type statement is usually that if the Hausdorff dimension of a set is bigger than something, then the Lebesgue measure of the distance set is positive. But the truth is in every, and I don't mean most, in every paper about the Falconer distance conjecture, one ends up proving a lot more. In other words, what one ends up proving is a quantitative statement that if the energy integral, which measures the Hausdorff dimension, is bounded, then the Lebesgue measure of the distance set is bounded from below by another positive constant, which can be estimated in terms of an upper bound on the energy. Okay, so suppose that you have a statement of this type. Then the key observation, and this is not a difficult calculation to make, but the key point is that if you compute so this is a continuous energy of these measures mu sub ns. So remember what they were. So this was taking the points, thickening them, and dividing so that it's a probability measure. So if we want the continuous energy of these measures to be bounded above independently of n, then a very simple and direct calculation shows that this happens if and only if the discrete energy is bounded above independently of n. So the assumption on the discrete energy ensures us that we can apply the continuous result under consideration. The question now is, how do we apply this result? Okay. And this brings us to the final step. The idea is, suppose we want to compute the Lebesgue measure of the distance set of E and S, where E and S is this thickened point set Pn. Well, if we measure distances, there are two different scales. There's the tiny scale inside each little ball, and that yields intervals of length n to the -1/s. And then there's the large scale, where we need to compute the number of distinct distances between the centers of these balls. And this gives us an upper bound. But then we can turn this upper bound into a lower bound simply by multiplying both sides by n to the 1/s. And what this implies is that the number of distances determined by Pn is bounded from below by n to the power of 1/s. Okay? So what this says, roughly speaking, is that whatever is the best known dimensional threshold for the Falconer problem, the reciprocal of that number gives us a lower bound for the Erdos distance problem in the discrete setting. And a more careful examination of the same argument tells us that we actually get more. That it tells us that the number of n to the -1/s separated distances determined by Pn is bounded from below by n to the 1/s. Because in that argument, we don't distinguish distances that are separated by less than n to the -1/s. Okay, so this is the so-called entropy bound. So here, just as a sort of a very quick survey to finish off the talk, so the best known Falconer exponents in R2 is 5/4. So this was proved about 2 years ago by Guth, Wang, and myself. And in higher dimensions, it's d squared over 2d - 1. This is the work of Du and Zheng, also a couple of years ago. And in higher even dimensions, there is a small improvement, which is d over 2 plus 1/4. And this is by Du, Wang, and myself, Zheng, and myself quite recently. Okay, and plugging these into the mechanism described above yields a lower bound on the number of separated distances determined by sets satisfying the discrete energy condition. Okay, so now let me finish off the talk with a couple of observations about the comparison between what I just described and the known results. So in 2 dimensions, the Erdos distance conjecture is completely solved. So this is work of Guth and Ketz in 2011. In higher dimensions, the best known results, to the best of my knowledge, are due to Soimoshi and Wu. This is 2008. And I didn't write down exactly what they proved, but it's roughly, so the conjectured bound is n to the 2 over d, and they proved n to the 2 over d minus a quantity which is big O of 1 over d cubed. So in higher dimensions, it gets closer and closer to the conjectured bound. And these results are certainly stronger. If you plugged in the Falconer results into the conversion mechanism that I described, you'll see that these results are certainly better. However, there are 2 important points to be made. First of all, the results above were only proved for the Euclidean metric. So the Guth-Ketz method and the method used by Soimoshi and Wu relies strongly on the fact that we are working with a Euclidean metric. It used symmetries of the sphere in a very non-trivial way, whereas the arguments here are far more general. Okay, and another point is that the continuous to discrete conversion mechanism yields separated distances, and this cannot be obtained from the method employed in these discrete results because, roughly speaking, they rely on polynomial type methods which don't do very well under small perturbations. And I think I'm going to stop there.
Thank you, Alex. Questions for Alex? Unmute yourself and go ahead. Awe. Everyone is in awe.
Mm-hmm. Well, there were several questions during the talk.
Yes. So great, thank you. So next week, we have a speaker named Emma Bailey, who is a postdoc at the Graduate Center. She got her PhD at Bristol with some of our friends. And like many postdocs at the Graduate Center and elsewhere, she's in England because she can't come to America. So, so this is probably her first talk at CUNY, where she is on the faculty, basically. Wow, everyone is so quiet.
Actually, some questions were asked by private chat, but
yes.
I should say that I had some people also offer comments privately in support of your talk, Alex. So
okay, that's good. So because it's hard to throw tomatoes over Zoom.
I've been petitioning for the tomato emoji.
Oh, they need a tomato emoji. That's true. Oh, that would be fantastic. And thank you very much, Mel. It was a pleasure to speak at your seminar as always.
Great. Can you unshare the screen?
Oh, of course. I think I just did. 1 second. Stop sharing. Yeah, I think I.
There you are. Now, just so people can see each other.
Oliver, if you're still there, did I clarify your question about what PN is and how it all fits?
Yeah, perfectly well. Yeah, I guess you were just emphasizing that you wanted to consider all possible sizes of the set.
No, that's true. No, but some of it really were typos. I mean, the P versus PN, and I really was typing it while watching CNN. So this is, I'm not going to do that next time.
Were you watching CNN? Oh, you've made up your slides watching CNN.
No, I wasn't watching it during the talk. No.
No,
I
I
stayed
mean-
away. I don't know.
Some
Look, the
people
world
are obsessed.
I wouldn't know.
So Mel, how can we find these talks online, right? They get recorded and posted somewhere somehow.
Yes. So when we started at CUNY teaching online last March, I set up, so I had to, and it was supposed to be whatever it was. So I was giving my lectures on Zoom and recording them, and I set up a YouTube channel called Nathanson Math Lectures, where I have, like whatever I was teaching, calculus or PDE or God knows whatever the hell I might be teaching. So there are various playlists under Nathanson Math Lectures, and one of them is New York Number Theory Seminar. So usually within an hour or so of the end of a seminar, I will have posted the video on